Swayam Prabha. Digital India. Educated India.
Good day everyone. Today I will start the first lecture of the course Texture in Materials, that is Introduction to Crystallographic Orientation or Texture. Give me a moment, I will put the pointer on. So, today's course is on Introduction to Texture. The concepts that will be covered in this course are processing microstructure property relationship, what is texture, and information that we can obtain from the classical microstructures, and then quantitative microscopy. Let us start with processing microstructure property relationship. You know, polycrystalline materials that are minerals, metals, ceramics, semiconductors, superconductors are basically made up of aggregate of many small crystals. A material tetrahedron in metallurgy or material science is being used to show the processing microstructure property relationship of these materials. Now, the material tetrahedron is basically used to design the material through some kind of a processing method, and this processing method could be solidification, which is basically known as crystallization, that occurs from a non-crystalline or a liquid state to a solidified polycrystalline state, phase transformation, a transformation from a different crystalline state to another crystalline state, say from face centered cubic to body centered cubic, or from hexagonal cubic to body centered cubic, or vice versa. Plastic deformation processes, that is by slipping of dislocations and formation of twinning leading to obtain a different kind of microstructure, and other methods like recrystallizations which occurs in a same phase by reducing the stored energy of the material. So, processing of the material is being done to obtain a desired property, so that it can perform or it can give performance under circumstances which is basically in structural field, or in case of these that are needed, or magnetic properties which are needed, mechanical properties that are needed. Now, you see, the processing of the material not only changes the microstructural morphology, but it also changes the texture. So, as the processing involves change in both microstructure and texture, the texture must be considered while considering the property changes in the material through any kind of processing available. So, you see, what do we know, what do we understand by microstructural morphology? You see, microstructural morphology shows the size of the grain, the shape of the grain. It shows the dislocation characteristics, such as how the statistically stored dislocations are present, they are in large quantity or they are in small quantity, what is its density. The presence of geometrically necessary dislocations could be understood. The character of the secondary phases and the precipitates present are also important while characterizing the microstructural morphology. Now, however, in classical metallurgy, you only considered these aspects, but we forgot the aspect about taking into account the texture. Microstructural morphology and its characterization must also include info of crystallographic orientation and misorientation, which is basically texture. Misorientation, on the other hand, are basically related to grain boundary character, which could be related to the special coincident site lattice boundaries and also to the geometrically necessary boundaries, which have smaller misorientation as compared to the grain boundaries. Now, what do we know? Polycrystalline materials are crystalline in nature. Most properties are basically sensitive to anisotropy. Crystal alignment and their associated anisotropy is usually ignored in classical metallurgy. Microstructure must include crystallographic orientation, which is basically known as texture. The question comes that what is texture basically? So, as I said that polycrystalline materials are basically aggregate of many small crystals that are present inside it, and you can see this figure which is of pure titanium, and you can see that this microstructure contains many grains and they are shown in different color, and they are shown in different color because they were taken from ACM scanning electron microscopy based electron backscatter diffraction technique, which is basically a quantitative microscopy. These colors are not random colors. These colors represents the color with respect to a specific orientation, that is the specific crystallographic plane perpendicular to the screen. And you see that there are few green grains which are basically representing two 1 bar 1 bar 0 plane, blue grains which basically represents 1 0 1 bar 0 planes, and these could be tallied with respect to this color key code, which is, and this is basically the IPF inverse pole figure code, and we will talk about these things later in the part of this course. So, you see that crystals which are normally referred as grains are basically orderly array of the motif or basis of atoms in space. This atomic arrangement inside the crystal is known as crystal structure. The smallest group of atom possessing the symmetry of the crystal is called the unit cell, and this could be FCC, that is face centered cubic, BCC, that is body centered cubic, hexagonal closed packed system, HCP, etc. When unit cell is repeated in all direction, that is periodic arrangement of the unit cell could develop the crystal lattice. So, you see that whenever the unit cell is repeated in space, in 3-dimensional space, it produces a crystal lattice. The limited volume of the material in which the periodicity of the crystal lattice is maintained or present is basically known as the crystallite. In ideal situation, a grain is basically should be equivalent to a crystallite unless and until some kind of misorientation is present inside the grain. And you must know that all grains have an hierarchical structure, and they might have subgrain cell structure inside the grain. They might have some geometrically necessary boundaries made up of arrays of dislocations inside the grains, and therefore, in real life scenario, a grain could be made up of many crystallites. So, you see that what I am trying to say, that the periodic arrangement may not be maintained within a grain, but could be maintained in parts of the grain through some divisions which are basically boundaries, but not grain boundaries, have misorientations which are lower than the grain boundaries and basically known as the geometrically necessary boundaries. So, each of these crystallites has a specific orientation of the crystal lattice, and therefore, these crystallites when present in a polycrystalline material produces a microstructure which consists of texture. Now, texture comes from the Latin word which is textor, and which means the weaver, and in material science texture is the way by which polycrystalline material is basically woven. So, if we define texture, texture is concerned with a specific structural feature of polycrystalline material, the crystallographic orientation. That is the position of the atomic planes and direction of each crystal volume, that is crystallites, relative to the fixed sample reference system. Here the word relative to the fixed sample reference system is very important. The physical properties of crystal normally depend strongly on the direction along which they are measured. The polycrystalline material, individual single crystals have specific orientation. Some grains with nearly same orientation and others with various orientations, and therefore, they are textured materials. So, you see, so texture is a very important part of the microstructural morphology that usually in classical metallurgy it is ignored. In classical metallurgy, from a optical on an SEM image like this, which is shown, and the microstructure shows equiaxed grains, and you see from this optical or an SEM image like this, we can obtain that what is the grain shape, and we can do a linear intercept measurement, or we can measure the area of each grains using some kind of software and find out that what is the grain size or an average grain size of the material. We can even found the the grain size distribution, but these will be done by manual method, and even we can find out that what is the grain boundary fraction in this microstructure. But you see that we will not able to quantify appropriately, first of all, properly the grain size distribution. Secondly, even though we can find out the grain boundary fraction, we will not be able to find out that what fraction of grain boundary is of what misorientation. That means the deviation between two grains separating out by that grain boundary, what is the angle of deviation, what is the axis of that deviation, we will not be able to find. And therefore, analysis of texture and quantitative microscopy basically is required in order to understand more deeply the microstructural morphology. Here I am showing another rolled alloy, magnesium alloy sheet, and you can see it is a colorful microstructure again, but as you can see that this colorful microstructure basically represents the quantitative microscopy, and the colors represents the plane taken, and one can relate it with the triangular color key code and can tell that okay, most of the microstructure are along 1 0 1 bar 0 and 2 1 bar 1 bar 0 planes. And therefore, you see, if we look into this microstructure, we can get many information more apart from grain size or the grain shape or the grain size distribution, which can be very appropriately calculated, but we can also get the information of a texture. This is a 0002 pole figure, and please don't get confused with the pole figure certainly, and we will come to it, and slowly you will see that this is just another tool, another scale to measure the texture. And so, pole figure is basically a scale to measure texture, and you see that the 0002 poles are in both the directions, and therefore, we can measure the texture actually. So, we will come to this in very detail, and you will see that this is so simple. Now, from the quantitative microscopy, we can do a very nice grain boundary map, and we can show that what is the distribution of grain boundary, and see we have colored the map, the grain boundary map, into red, green and blue color based upon our what it helps us, and we do like that to solve the problem. So, you see that red color boundaries are mapped, the misorientation angle of these boundaries are 2 degree to 5 degree. The green color boundaries are basically 5 degree to 15 degree, and the blue color boundaries are 15 degree to 180 degrees. So, you see that we can map the boundaries and color them basically, that is to quantify them on the basis of their misorientation. We can say that okay, the 2 to 5 degree boundary fraction is 0.15, the 5 to 15 degree boundary fraction is 0.022, the 15 to and higher angle boundaries are 0.825, and we can give the number of the boundaries, the length of the boundaries in micrometer, in centimeter, etc. We can find the misorientation angle between the boundaries, and then we can distribute them and show their number fraction. So, we can obtain a very quantitative information of the microstructure, not only very detailed, very vivid, but we can use them and correlate them with the mechanical property or the deformation behavior or phase transformation or solidification technique, annealing mechanisms, and we can get a more in-depth analysis from this information. So, we see that not only that, but we can find out grain boundary characters from this microstructure, because that is a quantitative microscopy, and then we can find out the presence of coincident site lattice boundaries. And here is the figure showing the coincident site lattice boundaries from another microstructure, not this one. And we can see that there is a large presence of sigma 3 boundaries, and then there are presence of sigma 11, sigma 25 b and sigma 33 c boundaries for that material. And this is basically done over a steel sample. So, we can get much more in-depth information about the quantitative microscopy by this method. So, you see here is another information that we can obtain, that here is a microstructure quantitative microscopy obtained by scanning electron microscope by the electron backscatter diffraction method. And this is the microstructure of pure titanium, and this is a biomedical grade titanium, and we are doing an in-depth work on this. We are understanding that how to increase the strength, so that a thinner section could be used in the body of a human being when it is required, without alloying them with vanadium and aluminum, which is usually used commercially. So, you can see that these microstructures have various grains, and each grains are of different color, and this could be mapped with the help of inverse pole figure, color key code, triangular color key code that I have shown in the earlier slide, but I have not shown it here. We can not only show that, but we can also find out what is the orientation or what is the relationship of the unit cell with respect to this microstructural important reference system. And let us say that the microstructure's important reference system is the horizontal one, which is x, and the vertical one, which is y, and with respect to that you can see, if I choose a grain 1 and it has a orientation which is like this with respect to the x and y. If we choose a grain 2 and this is this one, and basically this is, you can see that this is a small twinning that had occurred inside the grain 1, and you can see that twinning leads to the rotation of the unit cell by nearly about 90 degrees in this case. And you can see all this orientation of all the different grains, and we have marked it with respect to the number of the grains. So, we have serial number of the grains with respect to the unit cell. So, you see that we can not only get information of the overall orientation of the material, that is a cumulative orientation or cumulative texture of the material, but we can obtain information from each and every point, each and every pixelite of the material. And therefore, you see that in this case the researcher has obtained information of the unit cells or the orientation for each grain, and which is an extremely in-depth information. On the other hand, you see a line has been drawn in the grain number 10 and we have measured that the misorientation between these grain boundaries, and we have found out that misorientation is nearly 85 degrees, and you see that we can even find out the size of the grain in between them. Finally, we can conclude that processing of a polycrystalline material involves development of not only microstructure, but also crystallographic texture. Texture is a very important microstructural property in a polycrystalline material and it cannot be ignored. Texture is the relationship between important crystallographic planes and directions of a single crystals of those single crystals with respect to important sample reference directions. Texture involves crystallographic orientation and misorientations. Misorientation include geometrically necessary boundaries and grain boundaries. Thank you.